All right, so I guess it's the time to start. So today we have Nikita Rao who will talk about CatLM. And Nikita, you have the floor. Please start.
Thank you, Misha. So, hi everyone, I'm Nikita, and I guess we can jump right in. So, we all know that testing is an integral part of software development. In well-tested projects, you generally have code files which are paired with at least one test file to evaluate the functionality of the code. However, writing tests can be time-consuming and is often neglected. So this has led to extensive work in automated test generation. And in our work, we are looking at automating test generation using large language models. So some of the tasks that we are hoping to solve with this is the task of test generation, firstly. So given a partially complete test file and its corresponding code file, the goal of test method generation is to generate the next test method. And developers can use test generation to produce either the entire test suite or add tests to an existing test suite to test for new functionality. So given some code context, we evaluate our system in 3 different settings. The first is first test generation. So here, the first test of the file represents the beginning of the developer's testing efforts. And in this setting, we assume that all the basic imports and high-level scaffolding are already in place, but no test cases have been written yet. The next case we look at is the last test or final test of the file. In this case, we're assessing the model's ability to infer what is missing from a nearly complete test suite. So we evaluate this ability only on test files which have 2 or more human written tests in order to avoid cases where only one test is appropriate in the file. We also look at an additional setting called the extra test generation. So the extra test or the additional test investigates whether the model can generate new tests for a largely complete test suite. But in practice, this might be unnecessary and may not necessarily actually contribute to the coverage of the test file, but we wanted to check if the model can, in fact, generate tests based on what is missing in an already complete test suite. We also look at test completion. So the goal of test completion is to generate the next statement in a given incomplete test method. So here the goal is to help developers write tests more quickly. Now, just to motivate our setting a little bit, language models have been trained on code, and these can be used to generate tests that are very similar to those written by humans. But current models are trained to generate one file at a time. And this is standard practice in natural language processing. But because of this, they fail to consider the code under test context when generating the test file. And we know that as developers, when we are writing some tests, we usually look at the code. So the relationship between code and test file is important. But existing models are trained on separate files, and so they can never learn the dependency between them. Our goal is to demonstrate the importance of incorporating domain knowledge when building models. So in this case, it's the relationship between code and test files to create more powerful models for automated test generation. And the way we do this is by using aligned code test file pairs. We introduce a new token called the code test pair token. And we basically concatenate the code file contents along with this token and the test file contents. So this forms a code test file pair, and we use this for training. So in this way, we are forcing the model to sort of learn or look at the code that is present when generating the test. So just to give an overview of the whole system, we first mine data from GitHub and pre-process the data that we collect, which we then use to pre-train CatLM. The pre-trained model is then used to generate tests, and we evaluate this test using a software testing framework. This is a high-level overview of the entire system with the data pre-processing steps, the pre-training, evaluation, and I'll go into each one of these in more detail. So let's first start with the data collection and pre-processing. So we mine data from GitHub. We first query and clone GitHub archive to get Python and Java projects. This results in roughly 23 million files. We then apply a couple of filtering and deduplication steps, and this results in 15 million files. And lastly, we align the code test file pairs, and we end up with 1.15 million file pairs. So I'll go into depth into each one of these steps next. For data collection, we use the GitHub API to mine repositories having at least 10 stars, and these repositories should have had a commit after January 1st, just to make sure that the repositories are not stale. We also deduplicate all the repositories by removing any forks that are present. As a result of this, we end up with roughly 150,000 Python repositories and close to 50,000 Java repositories, which together have 23 million files, which is roughly 280 GB of data. We do a random test train split here, and our test set includes 500 repositories that were picked at random from each language. So we have 500 for Python and 500 for Java in our test data set. To prepare our data for training, we first remove all non-source code files. This includes things like README, config files, data files, and etc. We also apply a bunch of filters based on code parrot standards in order to make sure our data is not very noisy. So some of these filters include removing files that are larger than 1 MB or have lines that are longer than 1,000 characters, or have more than 25% non-alphanumeric characters, and some indicators of being automatically generated. After applying all of these filtering steps, we do another deduplication step by checking each file's MD5 hash against every other file in the corpus. So at the end of this, we end up with roughly 15 million files. We then do the code test pair alignment. So in order to do this, we first need to extract all the code test file pairs from these projects. And we do this using a combination of exact string match and fuzzy string match. So we look at the code file name and search for any test file that has the keyword test as a prefix or suffix. And if there are no matches found, we do a fuzzy string match and accept any pair which has a similarity score greater than 0.85. Once we have extracted all the code and the corresponding test files, we combine them in the way I explained before, where we take all the contents of the code file, use the code test pair separator, and then append all the contents of the test file. So this results in a total of 1.15 million code test file pairs, out of which 400,000 are from Python and 750,000 are from Java. Here is just a distribution of all the code test file pairs we found along with the code files and the test files. So in total, we have close to 11 million code files for which we did not find a corresponding test file. We have roughly 2 million test files and 1 million file pairs. So this also includes an example of what the code test file pair looks like with the content of the code, the special token that we introduce along with the content of the test file. There's probably more an opportunity here to extract other test files, but this just becomes more challenging unless you actually build the code and do more sophisticated matching. We also analyzed the distribution of all the data that we collected. So here, the projects have been sorted by GitHub stars, and they have been grouped into percentiles and just normalized so we can see the trends better. So upon manual inspection, we found that generally popular projects tend to have a higher star count, tend to be better tested, so they have more test files in them. And we also found that
Sorry, I'll fix that in a sec.
לא איזה 8, תרח מזה. מה פתאום, 8 אתה עולה לישון אחרי שאתה אכלת.
Yeah, sorry.
can I continue?
Yes, please. This was a participant. I think this seminar is advertised broadly, so it's not from JetBrains, as far as I know, who forgot to mute their microphone. So yeah, please continue, Nikita.
Oh, okay. Yeah, no problem. I just wanted to make sure that wasn't a question. So upon analyzing this data, we also found that Python has roughly 3 times more projects than Java, but Java has nearly twice as many code test file pairs when we then have the execution setup for our testing framework. So for Java, the projects can use different Java versions, including version 8, 11, 14, or 17, and they may have different build systems, including Maven and Gradle. So we manually configured Docker containers for each of this combination and executed all the projects that we had from our test set. We do exclude projects where we could not extract code file pairs. So in the end, we end up with 97 projects that we try to execute, but we were only able to successfully build 54 out of those. And in those 54 Java projects, we have 61 code test file pairs. We do something very similar for Python, where we manually configured Docker containers for Python versions 3.8 and 3.10, along with the PyTest framework. Here again, we excluded projects that did not have code test pairs, so we end up with 152 projects. And out of the 152, we were able to successfully build only 41 of them. And these 41 projects have a total of 1,080 code test file pairs within them. To prepare our test data, we additionally exclude any pairs where you only have a single code or a single test method in the whole file. We also ensure that these projects are compatible with Jacoco and Coverage, which are coverage libraries for Java and Python. And as a result of this, we end up with 27 pairs across 26 projects for Java and 517 code test file pairs across 26 projects for Python. In Python, we did notice that there was a bias towards larger projects where the top 2 projects had 346 tests in them, or test pairs in them. And in order to reduce bias towards these projects, we sampled 10 pairs from each of those projects. So in the end, we end up with 123 pairs across 26 projects for Python. This is the final test set that we do all our evaluation on. Now, moving on to the pre-training steps for CAT-LM. First, we look at the input representation. So since we introduced the new code test pair token, we have to train our tokenizer from scratch. And we trained a subword tokenizer using the sentence piece toolkit with a vocabulary size of 64,000 tokens. In order to train this tokenizer, we use over 3 GB of data, where we randomly sample 10 lines from each of the 14 million files that we had collected after all the filtering and the forming the pairs. We then ended up plotting the distribution of tokens in just the code test file pairs. So this is the intersection from the Venn diagram that I had shown earlier, if you remember. So upon plotting the distribution of tokens, we find that most of the current code models have a token window of only 2000 tokens. And this barely covers all the data that we have. So for CAT-LM, we chose to train the model with a longer context window of 8,000 tokens. However, a longer context window does imply that you need more compute. And using a longer context window of 8,000 tokens allowed us to use more of the code test pair data that we collected. Just to give some background about different modeling paradigms, you could either train a model from scratch. In this case, you have some training data and you train the model and then you query this model based on whatever task you want to do. Another option is to have a pre-trained model that was pre-trained on a large amount of pre-training data. And then you fine-tune this model on for your specific task using the training data that you have. And you can then query this model. The last option, which has become quite popular these days, is pre-training with prompting, where you have this really large pre-trained model that was trained on a lot of data, and then you prompt it with few training samples along with your input query. So for this work, we focus on the pre-training and prompting paradigm. We use autoregressive language modeling for pre-training our model. Here's an example of what that looks like. So the goal is to predict the next token based on your past context. In order to train CAT-LM, we also introduce a novel pre-training signal for test generation, where we use the code context when available. So we not only use the 1.15 million code test file pairs that we have, but we additionally use all the other code files that we collected along with all the other unmatched test files that we have. So this helps the model not just learn the relationship between code and test files, but also learn general coding and testing behavior from the rest of the files. So to pre-train CAT-LM, we use all the data that we have, and CAT-LM is pre-trained using the autoregressive training signal. We have a decoder only, which is decoder only model, and it's a 2.7 billion parameter model. It's a transformer. So going into some of the actual modeling and training details, we had a compute budget of $20,000 in cloud credits. And based on this compute budget and the amount of available training data that we had, we looked at chinchilla scaling laws, which suggests that the maximum, given a fixed compute budget, you can minimize the training loss by training the model with at least 20 times as many tokens as the parameters. And based on some preliminary runs, we determined that based on the budget that we had, which was $20,000, and the training data that we had, we figured that an appropriate model size would be 2.7 billion parameters. And our goal was to train it with at least 54 billion tokens. We used the GPT-NEOX toolkit, which is based on Megatron and DeepSpeed. And we also use data parallelism to make the training more efficient. Since we have a larger context window of 8K tokens, we make use of flash attention for faster training. So our model architecture is, it has a 2,560 dimensional 32-layer transformer model, where our context window is 8,000 tokens. Our batch size is roughly 256.
Nikita, so
Yeah.
There is a question from the chat from Timur, who asks, why didn't you use some kind of already trained model? You did mention that you needed to have another tokenizer, but yeah, maybe you want to add some skills.
Yeah, so we chose to pre-train our model from scratch because we wanted to highlight that a lot of the existing pre-trained models don't use this relationship between code and test, and we needed our model to learn this relationship. And that's why we decided to start from scratch. And also the token that we introduce is not present in existing models. So we could not just start with like pre-trained weights.
Okay, thank you.
Are there any other questions?
Not in the chat, but
Okay.
folks, if you have any question, please raise your hand or write in the chat. Yeah.
Okay. I'll continue and you can interrupt me if there are other questions. So we use a batch size of 256 sequences, which translates to nearly 2 million tokens. And we train our model for a total of 28,500 steps across 18 days. There's a small caveat here, which I'll get into, but this particular version of the model was trained on 60 billion tokens, which we did hit our goal where based on Chinchillah's laws, we wanted to reach at least 54 million, and we reached 60 billion tokens during our training. So the small caveat here is after this paper was published, we got an additional grant of $5,000. So we ended up further training this model to 35,000 steps. And the checkpoint that is now available on Hugging Face is the latest model with the 35,000 steps.
Yeah, sorry, one more question we got, which is still on the pre-training. Did you try to add any token to the already pre-trained model and then fine-tune? That's what Alex asking.
No, we did not try that. So we only had 20,000. So we only had like $20,000 in terms of like our compute budget, which was part of a grant. So we only had one shot of training a model, and we couldn't really experiment with different strategies.
Thank you.
So for our compute, we ended up using 8 NVIDIA A100s GPUs with 80 GB memory, and this was trained on a single machine on Google Cloud Platform. So once we pre-trained our model, the next step is to prompt CatLM to generate outputs based on some context. So given some preamble of a test, since CatLM is it has been trained to using a left to right autoregressive pre-training signal, it can just be prompted to generate some code based on the preceding context. So given some preamble of some test code, you can have it generate the first code, the first test method, the last test method, and potentially an extra test method. You can do the same with an incomplete test for test completion. And we prompt CatLM with both the with and without the code context. So we end up with 6 different cases where you have the first, last, and extra test method generation with and without code context. And we use the same strategy for test completion, where we prompt the model with an incomplete test file with and without the code context. Now, you can prompt CatLM using this to generate your test methods, and sampling multiple outputs becomes very inexpensive. This is because the size of the method is relatively small compared to the context size. And this allows the model to efficiently generate multiple methods from some encoded context. We can then filter out any tests that don't compile, lack asserts, or fail by executing them in the testing framework. And the same applies to the test completion scenario as well. Are there any other questions about training before I get into the evaluation part of it?
Yeah, so a question from Mishane, which is why didn't you try to use some pre-trained model just as a some kind of initialization?
So that's because like a lot of pre-trained, so all the pre-trained models that exist right now have been randomly trained on code and test files, and they don't capture the relationship. Our hypothesis is that if you pre-train a model which explicitly captures the code and test relationship, then these models tend to perform better. And the only way we can test this hypothesis is by training it from scratch.
Just a sec.
Oh, sorry. Oh, is it okay to ask?
Yeah, sure.
Yeah, thank you. So the question is, you know, if you use any kind of pre-trained model, even if you extend the vocabulary or etc., so for the same compute budget, you will get presumably a better model, just because it already has some knowledge, and you just fine-tune it in the, you know, to fill it with all the things you mentioned.
That is true. I agree that for a given specific task, it is helpful to just fine-tune it for whatever your task is. But our core hypothesis was that the way models are trained right now is not incorporating domain knowledge when they should be incorporating domain knowledge. And when they have been pre-trained on a lot of just random code data and random test data, then we just figured that we wanted to see what difference it would make to pre-train the model using this domain knowledge, which in this case is the relationship between code and test files. And the only way we can test this hypothesis from ground up to show how much of an improvement this gives is by pre-training from scratch.
Oh,
But I'm not saying that fine-tuning is wrong. It's possible that it would have done
you're
better.
training with your data, so it's not the end task, but you generated a lot of data, so you can just continue training on the data you collected and you pre-trained it, so you can treat it as continual pre-training. So you pre-trained the firstly on other data, so what's your initialization is, and then you just continue pre-training. So that's what I mean. But I understand. I understood everything. So thank you. Thank you.
Yeah, I guess the two main reasons we didn't is because we wanted to test the difference of like, and the scale of the difference would be more apparent if you pre-train it from scratch. And also the pre-training signal is different with the extra token. So that's why we just ended up doing it from scratch instead of trying to fine-tune it. And again, we were very limited by our compute budget. So we only had one shot at it. And we just decided that it made more sense to train from scratch to test this hypothesis, and like future work can potentially build on this with like other models or like tuning other models. Okay, if there's no other questions, we can move on to the evaluation setting for Catalan. So we have two different tasks, the test method generation and the test completion. So for test method generation, we look at the code-gen models as well as star coder model. For code-gen, we look at both the multi-model, which was trained on multiple programming languages, including Java and Python. And we also look at the mono model, which was further fine-tuned on a Python corpus. And the largest, so the 16B code-gen mono model is said to be comparable to Codex, and that's why we ended up using that. The star coder model, on the other hand, has been trained on close to 80 programming languages, which includes Java and Python. And in this case, star coder does have a larger context window of 8,000 tokens. And it was trained using the fill-in-the-middle objective on 1 trillion tokens of code. Coming to the metrics, we look at both lexical and runtime metrics to evaluate the generated tests. So the goal of using the lexical metrics is to measure the lexical similarity between the generated test and the human written ground truth. We look at scores like code blue, exact string match, and Rouge for this. And we also look at runtime metrics to measure the utility of the generated tests. So we look at the number of generations that actually compile and pass the test suite, and we also compute the coverage of these generated tests. So to prepare the input for the model, we use an ASD parser to prepare partial test files. So for the first test case, we only include the prefix of the test file and exclude any test methods. For the last method, we include everything in the test file but the last test method. And for the extra test, we just include the entire test file. We also compute baseline coverage on the human written test for the first and last test case, so that we can compare the coverage of the methods that were generated by Catalan. The reason the extra test case is 0 here is because there is no human written extra test since, yeah, so that's why the baseline numbers for the extra test case is 0. Now, going into some of the details of how we actually use the testing framework. So once we've prepared all the test inputs, we feed them to Catalan and generate close to 10 samples for each setting. We use a temperature of 0.2 so that we get plausible but also diverse outputs. And then we take all the generated tests and put them back into the original test file. We then execute the respective project's setup commands and check for any errors. And we record all the number of generated tests that compile and that pass the test suite. We also compute the code coverage for all the passing tests and compare that with the human written test cases. We look at 5 different evaluation metrics or settings, I guess. So the first is coverage.
I'm sorry for interrupting. My name is Alex.
Okay.
I have a question. Yeah. So maybe I missed that part, but if you step back 2 slides, what is the data set you were running evaluation on? I mean, like suddenly we have the whole test suites and the commands that you're able to run to measure something. So I was a bit lost. Where those are coming from?
So this is all part of the framework that I talked about initially. So here, so we set up all the containers with different combinations of like Java versions and build systems, and we had set aside 500 projects for Java and 500 projects for Python. And we successfully built 54 Java projects that do have code test file pairs. And similarly, we built 41 Python projects where we had roughly 1,000 code test file pairs. And then we...
What was the indicator? How do you pick the projects that are buildable? Like you used heuristics like file names and presence of POM XML or...
No, we just tried... we randomly selected 500 projects.
Okay.
And out of that, we excluded the ones for which we could not extract code test pairs. And then we just manually tried to like run all of them using the different Docker containers that we had manually set up.
Given that they already have the known test pairs in them, right? That was the...
Yeah, this is the ground truth data. So you have the code file and the human written test file for these.
Got it.
But these were... Sorry, I was just going to say that these were selected at random just to make sure that they do not include in our training set. And we also had few additional filters, like to make sure it's compatible with Jacoco and the coverage libraries to be able to compute the coverage metrics on them. But this was all manually set up.
Got it. Thank you for explaining. Yeah, I somehow missed that. Thanks.
No problem. Let me go back. Okay. So we look at 5 different things for the test method generation evaluation. The first is coverage. We find that the tests generated by Catalan are comparable to those written by humans. And the coverage distribution for the first test and last test is almost the same as that written by humans, and they shared like very close medians and quantile ranges. In the last test case, the average of the coverage improvement is significantly lower, but this is because the baseline coverage is already pretty high in this mode. And so it's hard to generate a test that significantly improves on the coverage based on like the existing methods in the test suite. Wsimilarly, the extra test setting was especially hard just because the projects that we chose were very well tested, and they already had really high code coverage, close to 80% for both Java and Python. And so having the model generate an extra test that provides additional coverage was really difficult, even though Catalan did do it in a few cases. But there's no way of actually knowing if it's possible that none of these projects didn't really need that extra test because they were already so well tested and had a really high coverage.
Nikita, can you, maybe I missed that. What's the difference between last test and extra test? Can you explain to us?
So you have the developer written test, the code file and the test file, right? So you have a test suite. The last test is in your ground truth data, the last method that appears in your test suite or your test file. The extra test is one additional test that you're trying to have the model generate. So ground truth for the extra test setting does not exist. Basically, we just wanted to, the last test will check if given an incomplete test suite, can the model figure out what's missing and generate one last test to improve the coverage of that particular test suite. And the extra test is given an already complete test suite, can the model actually improve by suggesting some test that was missing that the human did not think of.
Okay, it's clear now. So this relies on the fact that whatever the human put in the ground truth, we assume that they've done a thorough job at writing achieving high coverage, and every single test method there had some role, so that you say, what if we remove the last test method there, and can we regenerate it again? Versus the other one, you say, well, but if you give everything that a human did and now try to go beyond what they did.
Yeah. And
Okay.
we're not
Then
assuming that the developer did
test,
well because
yeah. The
because
last
we
is the last in the file, or how did that, what's the last, how the one that you remove, like how did you pick one method or the last one syntactically in the file? What's the last one?
it's just the last test method in the file. So we use an ASD parser to figure out like which is the last test method.
Okay.
And since we have the human written files and we're able to execute, we actually can check, like we did run this and check that the coverage was pretty high. So we're not assuming that the developer written test suites have high coverage. We did run it and we found that they have 80%, which is pretty high.
So this last test configuration could have been might as well just pick randomly to omit any, if there were like 5 test methods, we could have picked number 3 or number 2 to eliminate. Okay, it's just that you pick an arbitrary order was the last one in the file.
Yeah, we picked the last one in the file because I guess we assume that developers are building on it in some way. So the last one is somehow testing for functionality that none of the previous ones tested for.
Mm-hmm.
But yeah, you could do it in an arbitrary manner.
Okay, thank you.
So the next thing we looked at was the pass rate. We found that Catalan generates more passing tests on average compared to all the code gen models as well as the star coder model, despite these other models being trained on a lot more data and being much larger in size. For Python specifically, we found that the first test setting is hard and all the models didn't perform super well. That's because the first test has the least amount of context to build on. But Catalan still outperforms all the other models in this case because it also had the code context in addition to the test context. Similarly, Catalan outperformed all the other models for the extra test setting. The last test setting was slightly different because we did see that other models in some cases did better than Catalan, and there is a chance that there was some data leakage in this case because all the CodeGen models and StarCoder model have been trained on a lot of data from GitHub, and it's possible that the projects that we have in our test set, these models have already seen during their training time, and there's no way we can confirm that or test for projects, I guess, where we know that these models have definitely not seen the test projects.
Oh, one question, please. So just let me turn the video. Okay. So you mentioned that Catalan with code context was tested on with the code context. So you extracted something related to so you extracted some files or some code that is kind of related to the test. Yeah. And what about other models? Are those also provided with the context?
No. So all the other models have been trained to only look at one file at a time, right? So we only give it the test context. So if we wanted to generate the last test for all the other models, we only give the test file up to the last text and then have the model generate the last test. But Catalan was trained to consider code context. So for Catalan, we would concatenate the code context along with the test context and then prompt the model.
Well, maybe so maybe you have heard about the repo bench. It's a benchmark for on repository level. So they are kind of trying to they're solving the same thing. They need some context to continue the code, and they're just provided this the context as a comment just above. So the all code goes above the code we need to complete, just as a comment with some markup, like this is the file from here named like this.
Right. Yeah, we didn't do that because these other models were trained in a specific way. And I guess our goal was to show that having a model trained with code context helps. And when you're doing test generation, you should look at code context, which other models don't do traditionally on their own. So for these baseline numbers, we did not do that. We just prompted the model the way we expected to, based on how it was trained, basically. So we only give it the test file context and have it complete the partial test file.
Thank you.
So Nikita, now I'm so thank you. So now I'm confused about the first test. So for Catalan, you gave the source, the code under test, the system under test. In that case, is the file, right? And then you ask generate me the first test. But for the other ones that you're not providing any context, any system under file, like how did you prompt it? What did you say? Like if the models, the CodeGen and StarCoder and those didn't get the system under test, like how could they generate the first test? That's what I'm confused.
So,
I must be missing something here.
yeah, so we don't just not give it anything. So in the first test setting, there is still some preamble from the test file. So we just exclude the test method. So any basically any helper methods or any setup code along with all the imports have been provided in the test preamble. So all of the models see that part. You have
Okay.
the preamble up to the first
import,
test method.
all the imports, all the setup, tear down,
Yeah,
things like
all
that.
of that
or
is there. We
helper
just remove
function.
we just remove the first test method or the first test case in the file.
And did you also keep the remaining test, or you didn't keep none of the so you just gave the preamble, the import and the setup and tear down and other helper
Yeah.
methods that were probably the developers created that infrastructure for testing the particular file. That was all the context, or did you give also some of you removed the first test, but maybe you gave some other tests?
No, we since these are like left to right train models, we only give the context up to the point. So
Okay.
nothing beyond.
Okay.
Because with the first test setting, our goal was to like help developers when they're just starting off, right? So they write the setup and the goal is to have the model generate the test suite for you or like generate the first test. So we don't give it the other tests in the file.
Okay.
But I guess the thing you mentioned about having other tests present, the last test setting sort of captures that because there you're also giving some additional test context.
So it's surprising to me that these models figured out for these particular import statements and for these helpers and set, because I would imagine not all test cases, not all the test input files contain a lot of that preamble. I would imagine that some did, some didn't do much. Some started right off, here is the test method number 1, test method number 2, and there's not a lot of preamble there. So
Yeah,
I'm surprised that actually this worked as well as it did.
That's one of the reasons we think there's like data leakage, because it's possible that all of these models have actually seen these projects. Since we just randomly pick projects from GitHub, it's possible that they were trained on it at some point, so they have some memory of it.
Oh, interesting. Okay.
We see similar trends with Java, where Catalan, along with the code context, outperforms all other models for all the cases. And here, the difference in the first test setting and extra test setting is more prominent. Especially with the extra test setting, Catalan generates nearly twice as many passing tests compared to StarCoder and CodeGen. Okay. Now looking at the impact of the
Niket,
code
I have a
context.
question. Is that okay if I
Yeah.
ask a question? So
Yeah,
about
sure.
this slide, so we can see that Cat LLM outperform all other models when making, generating passing test cases. So how about the failing test cases? So do you have any idea about the statistics, and also what are the reasons for fails?
I do. I have the actual numbers in like 2 slides. So
Oh, right. Okay. Sorry about that. Thank you.
yeah. Yeah, it's under lexical similarity and
Sounds
runtime
good. Okay.
metrics. So but let's look at the impact of code context first. We found that code context indeed helps CAT-LM generate better tests, and I guess it did outperform other models again. And there was a significant drop in performance on all other models which did not have this code context available. So this emphasizes that having the code context does help the model generate more valid tests, even though CAT-LM has been undertrained and all these other models have been trained for much longer, are much bigger in size, and have been trained on a lot more data than what we used. So looking at the lexical similarity, we find that CAT-LM has high lexical similarity scores, and these are often comparable or better than StarCoder, which was the best performing baseline. We don't have the lexical metrics for the extra test case because there's no ground truth available in those cases. But in general, we found that having context again does help. So I guess coming back to your question about the runtime metrics and whether they fail or not, we look at, these are absolute numbers of the number of tests that compiled and passed. And in the total on each column represents like how many tests we actually generated. So there were a lot of failing tests. Not everything that compiled passed, I guess. A lot of this could be because like the assert statements did not hold, or I guess they just did not really test what needs to be tested, and it's possible that I was just copying some of the code from like previous tests and stuff. But despite all of that, CAT-LM does outperform Cochin and StarCoder, and it does generate more tests that compile and pass on average. But we did find that the context does not really seem to help generate more passing tests in the extra test setting. This might be because the test suite is already pretty comprehensive, so the model can infer most of the information it needs from the test context alone, and having this additional code context does not necessarily provide it with any more useful data to help generate newer tests or like additional tests that pass. But I guess in general, our results support our core hypothesis that models of code should consider the relationship between code and test files in order to generate more meaningful tests. But I just wanted to pause here. Does that answer your question? Like, we did generate a lot of tests, but a lot of them did not compile and did not pass. So, but our numbers are still significantly better than the numbers of other models that do not look at code context.
So Nikita, if I'm reading this slide correctly, so let's say we read the first line, CAT-LM with context in the first test. So
Yeah.
there, in the Oracle, there were 270 for Java. There were 270 tests that you generated, out of which only 50 compiled, right? And out of which only 20. So it's roughly 10% of the ones that are generated by the LLM actually compiled and passed. So they were in the same equivalence class with they were the right test for that particular system under test, right? That's how we should interpret it.
Yes.
Okay.
Yes.
Okay.
But yeah, in terms of the numbers are like, yeah, only 10% roughly like actually pass or compile. But
Mhm.
I guess sampling is inexpensive. So if you know that only 10% is going to pass, we just generated 10 samples for each case. You could generate 100. So the likelihood of you finding a correct test that does compile and does pass increases significantly in that case.
Mhm.
And I guess with CAT-LM, this number is still double of what other models do. So it is a significant jump.
Yeah, yeah. So while it is a significant jump, to me, the higher level, I want to pop up a level, as they say in the compilers, from a point of view of someone, a developer, using LLMs to generate test code, if they have to sift, if there is a way to automatically sift 90% of the hallucinations, because those are would be if we call them hallucinations, right? If the code, if the test code doesn't even compile, or it's clearly, or it is some code that actually manages to compile. So when we get from 50 to 22, the 32 that we throw away still compile, but they are not exercising the system under test. They are it's either they show a bug because the test was not passing, or maybe you're saying much more likely the test was incorrect. The system under test was correct, but there was a hallucination in the generated test code, even though it syntactically looked okay. It was a hallucination. It was not exercising the proper, it didn't have the proper input that it set up, or what, for many other reasons it could have failed, right? So the bigger question, the higher level question is, if we are to use generative AI to generate test cases for developers, and 90% of the generated ones are hallucinations, we must have an automated way to filter those 90% of the hallucinations. It's easy to filter out the non-compilable ones.
Right.
I think it's a lot trickier to filter out the ones that fail because there's a hallucination in the generated test, versus the generated test actually failed and failed for the proper reason because there was a bug in the system under test. So that would be like the interesting research.
That's true. That is a really interesting, I guess that is true for any code LLM, because any model that you use for code completion or code generation, not just test generation, right? The likelihood of like the code that ChatGPT returns, for example, you can't always guarantee its correctness. So that is a problem, and we are not really solving that problem. But I guess in our work, something that does help with the filtering is the testing framework that we have set up, because we have set up these projects and we can execute these projects. So that does help us in filtering out anything that doesn't compile and doesn't pass. But it did require a lot of manual effort to set that up. But I guess as future work, people could, maybe you can further fine-tune CAT-LM by using just the tests that compile and tests that pass. So that way you have like a feedback signal where you could use either coverage or like pass rate and compile rate. All of these are useful signals. So you can do like RLHF style tuning of these models to further tune them and improve them, so they have a signal of like what a good test is compared to what like a bad test. That's one way you could improve this. Yeah, having a oracle definitely helps, but it is true. This is just, I guess this is like a very fundamental question that is true for any model.
And then the good news for us, for research, I guess that's why we are in business, is that when I talk with people, and I just gave a talk at a university, a seminar on generative AI as a programming assistant last week, And I sense that people have this fear, oh, generative AI, it's going to take our jobs as researchers, or the research that I'm doing is irrelevant, or the research that I'm doing is going to be replaced. And by, nobody's going to use my research because simply use generative AI to generate whatever my research is producing. And my message was that's absolutely not the case. Even if you look at your numbers, right? Generative AI has a wow effect, and you showed us that the number of tests that it generates and the coverage is equivalent to what humans could do. But there's a lot of work. You have to filter out 90% of hallucinations to get to that level of results. And that's where lots of researchers in the testing community, in the program analysis community, that's for us. It's how do we filter, how do we narrow that gap between, how do we remove automatically 90% of the junk so that we can truly get the 10% of the gems which are comparable to what the humans did, right?
That's true. There's still a long way to go.
Yeah. We are not going anywhere.
And I guess our work was just to highlight that you do need to look at the code file when generating the test, because this was something nobody did in the past.
Mhm.
But it's nowhere a solved problem, and there's a lot more people can do to improve on these numbers.
Nikita, so
Yeah.
if I may have a couple of questions for you. So okay, first
Sure.
technical one. That was the last slide for you, or you have something to?
I have a few more slides.
So yeah, let's continue with that because we have like 20 minutes left, and
Okay,
then I'll ask mine.
Sure, yeah.
Quickly
So,
ask a question.
Sure.
So it's a bit like in a paper you have like from industrial perspective, proprietary models set the state-of-the-art results, and then their open source model, and people are always kind of curious about the gap. And I can see that you have qualitative comparison with proprietary models in the paper, but I wonder why not here? Why not in this table?
I guess the biggest reason was like GPT-4 is paid, and we did not have the funding to actually run it several times across for all projects.
And then for the replication package that you share, which is absolutely awesome that you do, like what's your kind of guess? How hard would it be to add one? I mean, given that you have access and resources, would it be tremendously hard, or is it something that, quite easy to try?
It is super easy to try because the model is on Hugging Face. So all you need is 2 lines of code to import it from Hugging Face and like run it on whatever you want. So that's not hard at all. I have the links in future slides with a QR code and how to actually use the model, but it's literally just 2 lines of code. So it's super easy to try out the model if you're interested.
Thanks.
Okay. I have some more results on the test method completion. So maybe I'll like quickly go over some of those. And I do have some slides on the qualitative stuff too, but maybe I'll skip some of the details here. But for the test completion task, we looked at DECO model, which was the state-of-the-art model that was released in ICSI last year. And this is encoder-decoder style model, which is based on codified architecture. They make use of a couple of different things, including the method signature, prior statements in the test, and like the method on the test, for example, as their input. There was one small issue with comparing the performance of DECO on our test data because they apply a lot of filtering on their data set, which includes things like requiring JUnit and Maven and having a one-to-one mapping between the test and method under the code method under test. And so we could not really test that approach on our test data. So instead, we just picked 1,000 randomly sampled statements from their test data and evaluated CAT-LM on that. Here again, we looked at the lexical metrics that I talked about earlier. And In general, we find that CAT-LM outperformed Kiko across all lexical metrics with a significant improvement of like up to 40% improvement with CodeBlue. An interesting thing here is that the test context seemed more important for test completion than the code context. And so it just seemed like most of the necessary information that you would require to complete your test can just be found in the incomplete test method and file, and the code context does help, but not as significantly. We also did a small scale qualitative study where we just looked at a couple of different models, including GPT-4 and EvoSuite. And the goal was just to figure out like the benefits and drawbacks of the generated tests by these tools. And we basically just looked at whether different characteristics of the tests that were generated. So things like whether it was meaningful and the variable names made sense, or if they had good assertions and if the invocation of the method on the test was correct or not, and so on. We did this on an example with bank class, which included methods to add a customer, open an account, and print the summary of all accounts. So we found that CodeGen actually generates highly readable code, but these tests are often incorrect. Like here, get balance does not exist. So CodeGen just hallucinated it. EvoSuite, on the other hand, generates a lot of meaningless tests and has poor naming conventions and spurious exception handling. GPT-4 does generate high quality tests and with really which is readable and has good quality asserts. Similarly, like CAT-LM also generated pretty high quality tests with readable asserts. So some notes to remember though is that there is data contamination for GPT-4, CodeGen, and StarCoder models because they may have seen our test data at train time. Another key thing to note was the training budget. So all of these models have been trained on a lot more data, are much larger in size, and used a lot more compute than we did. So when modestly scaling up our approach could yield much better results and could beat these models potentially. Well, we already beat most of them, but like maybe we could also beat GPT-4. So just to summarize all the contributions, we released the data set of 1.15 million code file pairs that we collected, along with all the other cleaned up code and test files for both Java and Python. We also released the model. It's on Hugging Face. We also released the testing framework. So this can be used to evaluate any of the tests generated both by CAT-LM and can be reused in future work. And we did an extensive evaluation on various downstream tasks against strong baselines. Some key takeaways from this talk is that CAT-LM did outperform larger models trained on a lot more data with a much higher compute budget. The key insight here is that incorporating domain knowledge can fundamentally improve and help build more powerful models. So in this case, the mapping between code and test files does indeed help for test generation. CAT-LM is on Hugging Face. You should go try it out. It's only 2 lines. Well, I lied. It's 3 lines of code, including the import statement. But here's a summary slide, and you can scan that to, it will either take you to the GitHub repo or the Hugging Face page. I don't remember which one, but it's one of those, and they're both linked, so you can find the other based on that. But I guess to summarize, we pre-trained CAT-LM using a novel pre-training signal that allowed us to train on lots of data while ensuring that the code context is considered. And we experimentally showed that this does help outperform larger models trained on a lot more data on the task of test generation.
Thank you. Okay, thank you very much for your talk. And I guess I'll jump in with a couple of questions of my own. So could you please
Sure.
move to the slide with the results where you had compile and passing data? I think 58 it was, something like that.
This one?
Yeah, 57, yeah, this one. All right, so I have a couple of questions here. First,
Mhm.
did you have a chance to check what are the tests, what are the passing tests that you get, especially in the last test and extra test case? So one option could be that these tests indeed work, but they do not add much value. Like if the test is a copy or a mixture of all the existing tests, in this case, it
Right.
would give little value.
So that's actually true, and that does happen in the extra test setting. And the way we can figure that out is through, I guess this proves that, because for the last test setting, we were able to generate meaningful and useful tests that did improve the code coverage, and so it was, I guess, meaningful. But in the extra test setting, even though it was generating a lot of tests that did pass, those tests did not add to the coverage. And so it's possible that it was just testing functionality that was already tested in one of the previous test methods.
Okay, thank you. So
I can go back to the table.
yeah.
If that helps.
All right. All right. Second question is about the evaluation overall. So you consider like 5 different metrics to assess model quality, and in
Right.
general they do agree with each other. But like, what was the way you were looking at the results? So let's say you're somewhere, I don't know, in the middle of the training or stuff like that. Did you consider some metric to be like more relevant and some to be like, I don't know, more like an addendum, maybe useful to clarify some small things, but not the default one?
Right. So actually part of the reason we did end up, a lot of the prior work, if you look at them with test generation and with LLMs in general, they purely look at lexical metrics and just compare the generated code with the ground truth code. In our case, we didn't want to just depend on that, which is why we ended up putting so much effort into building the testing framework and actually executing the code and seeing if the code really works or not, because there's no point in getting some test method that looks very similar to the one that a human would write, but it does not run, that it's not useful. So for us, we thought that having runtime metrics is more useful, because this gives us more insights into whether the test generated actually work or not, or if it just looks like it will work, but have a lot of hallucinations and developers can't really use them. Because if you look at like some scores there, we're getting like 60-70%, which if you purely look at the lexical metrics, you might just conclude that, yeah, we're doing well, it's done. But when you actually look at the whether they compile and whether they pass, that's when you know that, okay, it's not doing as well as you think it's doing. It is readable and it does look like it was written by a human, but there is still a lot of scope for improvement, because the number of tests that actually pass and whether they really do add coverage, whether they are contributing to coverage or not, I think those metrics are more useful. And our hope is that by releasing the testing framework, future work can also make use of these metrics and actually execute the projects to see if anything you generate does actually run or not, and if that really does improve coverage or if it does pass or not.
Okay, thank you. And third question is about scaling for different things. So you mentioned you considered chinchilla work when you were
Right.
estimating what would be how to set up your model. So did you have a chance to look at the, I don't know, like loss graphs or stuff like that during the training phase to see how does the model capabilities improve, whether it would make sense to, I don't know, have another pass over the, or like another epoch, or maybe get more data.
So our loss curves did not converge. Our model is undertrained, and that's because we were heavily, I guess, constrained by the compute budget. We only had $20,000, so we trained it as much as we could until we ran out of the money. And then, so this is in no way like a really tuned, well-trained model, but we do see the advantages of having the code context in addition to test context, despite the model being undertrained, which is why when we got the additional $5,000, we did continue training it, and we did see the loss go down further, and that didn't converge either. But I guess part of being in academia is there are constraints, but yeah. So if you continue training this model, it's possible that it might do better than GPT-4. I don't know.
Yeah. Okay. Thank you. So, did you have a chance to check the first the first version of the model, which was trained only for $20,000, like to compare metrics? I don't know, compare loss. So just to have a hang on how much did it improve with training?
The loss did go down. I don't remember the actual numbers off the top of my head, but it did go down. So we know that the version of the model that's on Hugging Face right now is better trained in terms of like loss numbers, but that didn't converge either. So if you trained it further on the data, then it's possible that it will eventually converge and that model will be more powerful.
Okay,
but
thank you. Yeah.
Yeah, sorry, I just don't remember the actual numbers off the top of my head.
Oh, no, it's okay. All right. So any other questions, folks?
See that Alexandra has raised a hand and Misha has raised hands.
Okay.
Yep, I can jump in. Hello, Nikita. Thank you for a great talk and a very cool work. I have a quick clarification question. Sorry, maybe I missed it when you were talking about the data set, but I was curious whether you went for some specific testing frameworks. So for instance, for Python, there are like unit test, PyTest, and probably more. And did you settle on one specific, or did you include several? And yeah.
For training, no, but for testing, yes. We did end up using only projects that were supported by PyTest just because that was easier to set up and run. And we did not really try to do it with a lot of different other frameworks. I think with Java, we used Maven and Gradle, if I remember correctly. And yeah, we did use, I guess, to answer your question, we did use a few specific frameworks just because those were easier to set up, and just setting up all of those projects manually was hard and took a lot of time and effort. So we could not really spend too much time on that.
Yeah, sure. Makes sense. Thank you.
No problem.
Yeah, thank you. I have a question about the test collection. So it's very interesting. So you picked one heuristic that is kind of the name of the file and the name of the test, is it correct?
Yes. So we had two heuristics. It was a combination of exact string match and fuzzy string match. So in the case of the exact string match, we found that a lot of Python test files usually have like test underscore code file name or code file name underscore test. And similarly for Java, we found that they had the test prefix or suffix with the same name. So we first tried to do an exact string match. And if that did not work, then we did a fuzzy string match using Levenshtein distance. And if the distance between the two parts was greater than 0.85, then we assume that it's a pair.
Thank you. So, and the question here is, do you have any idea what are the precision and recall for this case? So we might get all the context tests, and every single context is correct. It is the case where it's precision 1 and recall 1. And we might get everything we needed and get some extra that is not related. It will be recall 1, precision 0.5, so something like this. So do you have any idea what are the
we don't have the actual numbers, but so the exact string match does automatically give you like high precision, because if there is a code file and the test file with the same name, then you know it's definitely a match and the test file is definitely related to that particular code file. But I guess with Python, we did see some examples where you can have one code file and multiple test files, in which case we would have just picked the test file that is closest, in which case we're not really capturing everything.
Maybe for instance, if they have the same name, but in the tests some other modules are used, something like this. So we might get something that is related to, but not all.
That is possible, because there might be some test file that makes use of multiple code files, and so the test file, I think we saw this with Python especially, where you can have multiple classes of tests for checking for different code files, and it's not great, but given that we were doing this at a really large scale, this was the easiest heuristic we could apply, and the only way we can make this much stronger is by actually building and executing all of it and like using parse trees or something. That makes it a lot more harder, and our goal was to get as much data as possible, but also get somewhat, if not like, I don't want to say not noisy at all. It's okay for the data to be a little noisy, which it is in this case, but we wanted to just maximize the data that we can get in the easiest way possible.
Thank you, very interesting.
So I want to ask another question. Nikita, this was a very nice talk. So lots of my colleagues from JetBrains on this call are working on different research that involves LLMs at some point. So I think this is an area where all of us can learn from each other. So I wanna ask more of a meta level question. This is a new kind of research or a new style of research that we are all setting up best practices. So it's not like, we've been doing compiler analysis or program testing for decades and everyone knows how to best design that kind of research.
Right.
So what are some of the best practices from, because you've done a lot of experiments with lots of LLMs and with your own, with your CatLM, what are some of the lessons that you learn from in this new genre of research, or in this new style of research, in this new era, I should say, of research that we are getting into which LLMs and generative AI play such a huge role? What are some of the things that you learn from your experience that you need to adapt your research differently, or you need to do differently with LLMs, that we can all learn from those lessons?
Right. I think that's a very interesting question, and I've been spending the past year or so just thinking about this, because when I guess Copilot and GPT-3 and GPT-4 came out, pretty much everybody in the world had an existential crisis where we felt like our research was no longer relevant and these models are going to take over everything. But I do feel like that is not the case. A lot of the models that are available right now, they tend to be like even with ChatGPT and like GPT-4, they're really good at like generalized tasks. But if you want to focus on a specific task that can help one group of people, they often don't tend to do super well in those cases. So there can be other issues, I guess. I actually have a slide on this that might be relevant. It's a bonus slide. But where I guess I was thinking a lot about just GPT-4 versus CAT-LM, for example. And it is possible that you might be in a company where you're working with proprietary data, in which case you cannot use these closed source big models and you have to train your own. So there is that whole line of research where you might have access to data that nobody else has, in which case building smaller specialized models for your data and your task does make sense. And also, like, I believe in open sourcing your things a lot. So I think there is still like a huge gap between models and like research that are available to public that is open source that other people can build on. And I guess the other thing that I've been focusing on for my research specifically has been to find a problem and to like, I still believe that you don't need models that are, I don't even know how large GPT-4 is, but you don't need models which are super large with billions of parameters. Sometimes it's okay for you to focus on the problem that you have and build a smaller model that works for your problem. And that's the direction I've been going in, where I just find problems that I think are relevant to developers and like focus on improving that and making that open source so other people can work on it. But I don't want to say that all of that research is useless, because I do think that you can still do a lot of things to build on some of the larger models. Like you can prompt it to collect data that you might need. So I think using these larger models as a technique for data augmentation for your research, like you might be working on a problem where data does not exist, and you can prompt some of these larger models to like generate the data for you and use that to tune a smaller model. So that's another direction that I think is interesting, and that's something I've been looking at too. So I feel like I believe more in like a developer first approach, where you figure out what problem you want to solve, what problems developers are facing, and then design solutions around that. And I don't think these large monolithic models are the solution. Like they do help in some cases, but especially for a novice audience. So say somebody is just starting to learn data science and starting to build ML pipelines and ML models, they might just copy paste the code that ChatGPT generates, but often these models still hallucinate. And I think for like novices and non-experts especially, just figuring out what is wrong with the code can be really, really difficult. Even for experts, I know so many of my friends who have like tried to use these models to like generate code, and it gives you a buggy version of the code, and figuring out what's wrong with the code often takes you longer than what it would have taken you to have just written the code from scratch. So I do think that there are a lot of research directions. You just need to find the problem.
Yeah, in a way, we don't have an existential crisis. I think the only people who are worried about their existential crisis are people who have not tried, who only believe the hyper in the media and all of that stuff, right? But all of us who, my PhD students have been trying, and we've been working, actively developing new solutions that are powered by LLM. So all of us who touched and work with this, we have no worry about our existence. Like we know that we have a reason to exist on this planet, on this earth, and in the research community, and the work that we are doing, it's extremely needed. And I think the bigger message for my colleagues at JetBrains is you are showing that you don't need these super large, fancily trained models, that a smaller model, even modestly trained, but that has access to the context, which we do have in the IDE, because we are the IDE provider. So we have context that nobody else has access to that context. GitHub or nobody else has the level of access to the context that we have.
That's true.
A modestly trained model with access to the context perform the same or even better than any your largest, fanciest models that don't have the access to the context. So that's a very nice message for us and anyone else who is in this space.
That's true. And I think code is also like a really interesting data source, because you have like documentation, you have comments within the code, you have like code reviews, you have a lot of things that I guess separates it from say like natural language, where it's more limited. You can execute the code and you can use all of these as signals to like improve your model.
Yeah. Thank you.
Thank you. So, folks, any other questions? Let's try to go to be brief, because we're already 7 minutes past the scheduled time.
I was going to ask you what's next, but that can also that's not a question that you answer in a minute. I say this is great work, and what's next? But yeah, for people who want to leave, I think it's okay. People want to leave, and if you want to stay and are curious to hear what's coming next on the research that Nikita is doing, feel free to do that.
Yeah, so I'm not really continuing this line of work, just because I think pre-training models require a lot of compute, and the only reason we were able to do this work was because we got that grant from Google and we got money. But now I've been looking at I'm looking at the problem of I guess bug fixing in a notebook setting, because notebooks are really interesting because you have markdown cells that like explain what the code does, and you can execute each cell and like use that execution information to it's just a really nice feedback loop that you can have. So I've been working on improving code generation in notebook settings, where we actually make use of this execution signal to send it back to the model as a feedback loop to improve on the code it generates. And we're hoping to train another small model, or like fine tune another small model and show that, again, smaller models can be helpful if you are looking at a very specific problem.
All right, thank you. I think that's a great message to end on. Like for problems that require a high accuracy, like not just generate some text, some documentation, but when we are working with code, then we need a high level of accuracy, right, and a high level of assurance. Smaller models in coalition with the code context and other contexts is very useful. And
yeah, definitely.
Okay, thank you. Thank you everyone for coming. Thank you, Nikita, for presentation. And this is it. Please subscribe to our meetup page, and we will